Furnaces are an important source of heat for many industrial facilities. Furnaces, which can also be referred to as fired process heaters, are basically enclosed structures that produce heat by the combustion of fuels. Although furnaces are used in a variety of applications, the basic components, operating principles, and operator responsibilities are similar for most furnaces. To become a safe and skillful furnace operator, you need a good grasp of the basics. In other words, you need a solid understanding of furnace fundamentals before you move on to specific operating procedures and responsibilities. So let's take a look at a typical furnace. This one consists primarily of a large box or shell and a stack. During operation, heat is produced by combustion inside the shell. The exhaust gases are routed to the atmosphere through the stack. In this furnace, the heat is provided by burners that are located in the floor of the shell. This type of furnace is a floor-fired furnace. Some furnaces are wall-fired, while others may use both wall and floor burners. In addition to burners, furnaces contain many other important parts. Inside this furnace, tubes carry the process fluid through the furnace. The process fluid enters the furnace in the tubes near the stack, passes through the tubes, and leaves near the bottom of the furnace by the burners. The tubes in this furnace are grouped into two major areas. This area, which is closer to the stack, is called the Convection Section, and this area, which is closer to the burners, is called the Radiant Section. The shell of the furnace is lined with a heat-resistant material called Refractory. Now let's look at some of the basic systems that furnaces rely on for proper operation. One of these is the fuel system, which delivers fuel to the furnace. A typical fuel system includes fuel lines and valves that carry the fuel to the burners and control its flow. On furnaces that use oil as a fuel, the fuel system also includes a fuel pump. Furnaces also need air systems. An air system is needed because the burners in a furnace mix air with fuel for combustion. Airflow to a furnace can be controlled in different ways. For example, on some furnaces, airflow is controlled by registers and by the stack damper. Air is drawn into the burners through air registers. The registers can be opened or closed to let more or less air into the burner. The stack damper is used to control the flow of gases leaving the furnace. This also affects the amount of airflow that can enter the registers. Opening or closing the damper increases or decreases the amount of air that flows into the furnace. In some furnaces, air circulation is accomplished using fans. These furnaces are called forced draft furnaces. In other furnaces, air circulation occurs naturally. These furnaces are called natural draft furnaces. In addition to the fuel and air systems, furnaces also have a process fluid system. This system includes the tubes that carry the fluid inside the furnace, and the pipes, valves, and pumps outside the furnace that move the fluid and control its flow. To keep track of all these systems, furnaces use instruments. Some of the instruments are located near the furnace, while others may be in a control room. Instrumentation and control systems allow operators to keep track of the overall operation of the furnace and to adjust operating conditions when necessary. Furnace control systems also have alarms that alert operators to abnormal conditions. Operators can then take action to prevent dangerous conditions from occurring. All of the parts and systems associated with a furnace are used to accomplish one basic task: heating a process fluid. We can get a better understanding of how this is done if we break the furnace operation down into three basic actions. In the first action, air and fuel are introduced into the furnace and then mixed together by the burners. The mixture is ignited at the burners. As the fuel burns, a chemical reaction occurs and heat is produced. In the second action, heat released by the chemical reaction created by burning fuel is transferred to the process fluid. The fluid flows through the tubes inside the furnace and receives heat by conduction, convection, and radiation heat transfer. In the third action, the combustion gases that are produced by burning fuel rise through the stack and are exhausted to the atmosphere. In this topic, we looked at some of the major components and systems that make up a furnace. We also looked at the basic operation of a typical furnace. Let's try some practice questions on this material. In a furnace, heat is produced by the combustion of fuel. Basically, combustion is the process of burning. In order for combustion to occur, 4 requirements must be met. Combustion requires fuel, air, heat, and a chemical reaction. When all 4 requirements are met, combustion will occur. Several types of fuel can be used in furnaces. Most often, the fuel is either gas or oil. Air is required because it contains the oxygen that is needed in order for fuel to burn. Heat is required to raise the temperature of the air and fuel high enough to make the chemical reaction possible. The chemical reaction is the actual burning of the fuel. When fuel, air, and heat are together in the correct proportions, the chemical reaction occurs. During furnace operation, the heat that's produced is transferred to the process fluid. Heat transfer occurs whenever there is a difference in temperature between 2 materials. When there is a temperature difference, heat transfers from an area of higher temperature to an area of lower temperature. Heat transfer can occur in 3 different ways: by conduction, by convection, and by radiation. Conduction is heat transfer as a result of physical contact between 2 materials, or heat transfer from one part of an object to another part of the same object. For example, conduction is the means of transferring heat across the walls of the tubes inside a furnace. Another form of heat transfer is convection. Convection is the transfer of heat within a fluid that occurs because of the movement of the fluid. Convection can be either of 2 types: natural convection or forced convection. We'll use this container of water and dye to show how natural convection works. When heat is applied to the container, the water that's closest to the bottom of the container is heated first. As the temperature of the water near the bottom increases, that water becomes lighter or less dense, and it moves upward in the container. At the same time, the water near the top of the container, which is cooler and heavier or denser than the warmer water, moves toward the bottom of the container. This is what happens during natural convection. As heat is transferred to the water, a difference in density is created. This difference in density causes the water to circulate in the container, and the circulation helps to transfer heat throughout the water. During forced convection, fluid movement is produced by a mechanical device, such as a pump or a fan. A good example of this type of heat transfer is the forced convection heating systems that are used in many homes and buildings. With this type of system, fans force warm air into the rooms that are to be heated. The warm air then mixes with the existing cooler air and heat transfer occurs. The third form of heat transfer is radiation. Radiation is the transfer of energy by electromagnetic waves. For example, the sun gives off large amounts of radiant energy in the form of electromagnetic waves. As the radiant energy travels through space, the waves that are in a direct line of sight between the sun and the earth come into contact with the earth. Some of these waves are reflected off of the earth, but others are absorbed by the earth. When a wave is absorbed, its energy is absorbed by the earth as heat. The amount of heat transferred depends on the number of electromagnetic waves absorbed. In a furnace, radiation, convection, and conduction are all involved in the transfer of heat from the burning fuel to a process fluid. The burning fuel produces radiant energy that travels through the combustion area or firebox. There is a direct line of sight between the flames and some of the tubes, and the outer surfaces of these tubes absorb heat from the electromagnetic waves that contact them. Radiant heat transfer is not the only type of heat transfer that takes place in the radiant section of the furnace. Some convection heat transfer also takes place. When the burners are firing, the gases near the burners are the hottest. As these warm gases mix with the cooler gases surrounding them, heat is transferred by convection. The tubes in the upper part of the furnace are not in a direct line of sight with the burner flames. Most of the heat transfer that takes place in this area occurs by convection, as the hot combustion gases pass around the tubes. This part of the furnace is called the convection section. Heat transfer by conduction also takes place in a furnace, as the outer surfaces of the tubes get hot and transfer heat to the cooler inner surfaces. Heat transfer by convection also occurs within the process fluid, as hot fluid inside the tubes transfers heat to the cooler fluid. In this topic, we discussed the 4 requirements for combustion, and we saw how combustion occurs inside a furnace. We also examined 3 ways that the heat from combustion is transferred inside a furnace. Now let's take a minute to try some practice questions on this material. All furnaces require a supply of air for proper operation. A furnace's air system ensures that the correct amount of air is delivered to where it's needed for proper combustion. The gases produced during combustion transfer heat to the furnace tubes and then flow up the stack. The flow of air and combustion gases through a furnace is generally known as draft. Furnaces are often identified by the type of draft that they provide. For example, 2 common types of furnaces are forced draft and natural draft. A natural draft furnace works much like a fireplace and a chimney. Heat from the fire in a fireplace warms the air in it. The heated air in the fireplace is lighter than the cooler air outside, so it rises through the chimney. This reduces the pressure inside the fireplace. As the hot air rises, it's replaced by cooler, heavier air in the fireplace, and the process continues. In a natural draft furnace, the hot combustion gases, which are lighter than the outside air, rise up the stack and create a lower pressure in the furnace. As this occurs, cooler, heavier air from outside the furnace is drawn into the burners through the air registers. Airflow through a furnace is produced by a difference in pressure. In an operating natural draft furnace, the pressure inside the furnace is less than the atmospheric pressure outside. As a general rule, as the difference in pressures increases, the amount of draft in the furnace also increases. The pressures in various areas of a furnace are typically measured by instruments called draft gauges. Draft gauges commonly indicate pressure measurements in units of inches of water. These gauges are used to determine the flow of air and combustion gases through the furnace. In a natural draft furnace, the height of the stack affects the amount of draft that can be produced. In general, if all other airflow conditions are equal, the taller the stack, the greater the draft. This is because a taller stack creates a greater difference in pressure. Often, the amount of draft must be adjusted for proper operation of the furnace. Since the height of the stack cannot be adjusted, another technique is used. In some furnaces, the draft is controlled by the position of a damper inside the stack. Changing the position of the damper makes the outlet for the combustion gases larger or smaller. As the outlet gets smaller, draft decreases. As the outlet gets larger, draft increases. Air and combustion gases are moved through forced draft furnaces by fans. This is a simplified illustration of a forced draft furnace. A fan, called a forced draft fan, draws air from the atmosphere and forces it into the furnace. On this furnace, the burners are mounted along one wall. The combustion gases flow through the furnace and then out through the stack. In a forced draft furnace, airflow is controlled by coordinating the positions and operation of the stack damper, the burner registers, and the fan. Some forced draft fans have dampers or louvers on the discharge side of the fan. These dampers can be opened or closed to allow more or less air to flow into the furnace. On other types of forced draft fans, the dampers are located on the inlet side. Adjusting the inlet dampers increases or decreases the amount of air that is admitted to the fan and into the furnace. Another type of furnace is a balanced draft furnace. A balanced draft furnace is similar to a forced draft furnace, but it has another fan in addition to the forced draft fan. The second fan is called an induced draft fan. It is located in the flow path of the combustion gases between the furnace and the stack. So, in a balanced draft furnace, one fan provides air for the burners, and the other fan removes the combustion gases. Furnaces are used to heat many different types of process fluids. As the process fluid circulates through the tubes inside the furnace, it receives heat that is produced by burning fuel. This particular furnace is floor-fired. The process fluid enters the furnace through these tubes in the convection section. This arrangement allows the fluid to be preheated by the combustion gases before it reaches the radiant section of the furnace. Preheating the process fluid makes it possible to bring it up to the desired temperature while burning less fuel. In other words, it makes the furnace more efficient. From the convection section, the process fluid passes through the tubes in the radiant section. The process fluid becomes hottest in the radiant section because more heat and higher temperatures are available. Regardless of the design of the furnace, the tube arrangement has to allow for a continuous flow of process fluid. For example, these tube ends are connected with tubing bends. In other tube arrangements, the tubes are connected together by enlarged sections of pipes called headers instead of tubing bends. The route that the process fluid takes as it flows through a furnace depends on the design of the furnace. Each continuous, uninterrupted path that the fluid takes is called a pass. This furnace is a single-pass furnace, but many furnaces are multi-pass types. The flow rate of process fluid through a furnace is regulated by valves. There's usually a control valve for each pass. These valves are often operated automatically as part of a control system. The proper flow of process fluid is critical to proper furnace operation. Flow problems can lead to heat transfer problems as well as equipment damage. One type of problem that can occur is called coking. Coking is the accumulation of carbon deposits on the inside walls of the tubes. Crude oil and some other types of process fluids tend to leave carbon deposits behind as they're heated and flow through the tubes. Coking makes the inside diameter of a tube smaller, and it can restrict the flow of process fluid. It can also lead to heat transfer problems. Carbon deposits insulate tube walls, which reduces the amount of heat that is carried away from the tube by the process fluid. If this situation is not corrected, the tube could overheat, weaken, and eventually rupture. Coking can also develop if the burner flames come into contact with the tubes. This problem is called impingement. Impingement can create hot spots on the tubes that can lead to the formation of carbon deposits. If the impingement problem is not corrected, the tubes could eventually rupture. In multipass furnaces, the flow of fluid through the tubes can present additional problems. In addition to flowing at the proper rate, the process fluid should move evenly through all of the tubes in the furnace. If the flow is not even in all the tubes, the fluid will not be heated evenly. As a result, the temperature of the fluid leaving the furnace may not be within the specified range. Also, if the process fluid moves too slowly in a furnace, the likelihood of coking and its associated problems could increase. In this topic, we looked at how air flows through natural draft furnaces, forced draft furnaces, and balanced draft furnaces. We also looked at how process fluid circulates through a furnace and at conditions that affect flow through the tubes in a furnace. Now let's try some practice questions on this material. Inside this furnace, tubes carry the process fluid through the furnace. The process fluid enters the furnace in the tubes near the stack, passes through the tubes, and leaves near the bottom of the furnace by the burners. The tubes in this furnace are grouped into two major areas. This area, which is closer to the stack, is called the convection section. And this area, which is closer to the burners, is called the radiant section. All of the parts and systems associated with a furnace are used to accomplish one basic task: heating a process fluid. We can get a better understanding of how this is done if we break the furnace operation down into three basic actions. In the first action, air and fuel are introduced into the furnace and then mixed together by the burners. The mixture is ignited at the burners. As the fuel burns, a chemical reaction occurs and heat is produced. In a furnace, heat is produced by the combustion of fuel. Basically, combustion is the process of burning. In order for combustion to occur, four requirements must be met. Combustion requires fuel, air, heat, and a chemical reaction. When all four requirements are met, combustion will occur. We'll use this container of water and dye to show how natural convection works. When heat is applied to the container, the water that's closest to the bottom of the container is heated first. As the temperature of the water near the bottom increases, that water becomes lighter or less dense, and it moves upward in the container. At the same time, the water near the top of the container, which is cooler and heavier or denser than the warmer water, moves toward the bottom of the container. This is what happens during natural convection. As heat is transferred to the water, a difference in density is created. This difference in density causes the water to circulate in the container, and the circulation helps to transfer heat throughout the water. One type of furnace is a balanced draft furnace. A balanced draft furnace is similar to a forced draft furnace, but it has another fan in addition to the forced draft fan. The second fan is called an induced draft fan. It is located in the flow path of the combustion gases between the furnace and the stack. So, in a balanced draft furnace, one fan provides air for the burners, and the other fan removes the combustion gases. This particular furnace is floor-fired. The process fluid enters the furnace through these tubes in the convection section. This arrangement allows the fluid to be preheated by the combustion gases before it reaches the radiant section of the furnace. Preheating the process fluid makes it possible to bring it up to the desired temperature while burning less fuel. In other words, it makes the furnace more efficient. From the convection section, the process fluid passes through the tubes in the radiant section. The process fluid becomes hottest in the radiant section because more heat and higher temperatures are available.